Hi, welcome to Chapter 5, Overview Part 2, where we're just going to talk about Section 5.5, Calorimetry. So what I'd like you to do now is pause the video and see if you could answer these questions. Okay, pause your video right now. All right, welcome back. So let's see how you answered these questions. How many joules of energy are transferred to each pot? Well, if you look up here, it says after heating for 5 minutes at a rate of 30 joules per minute. So 30 times 5 is 150 joules are added to each pot. Which pot is going to gain more energy? Well, you should have wrote neither, because they're gaining the same amount of energy. Which pot, if any, changes temperature more? Well, I would have wrote the 4-quart pot is going to change temperature more. And then it says, what factors determine how much the temperature changes? So I'm going to say the amount of water in the pot. How are these factors related? The more water you have, the smaller the change in temperature. So now let's look at this data. Pause the video and answer these questions. Okay, welcome back. It says, how much energy is added to each of the substances above? Well, that is 1,000 joules. Does this equate to the same temperature change in each substance? The answer is no. Explain why this is the case. Well, in this case, they both have the same mass, so we can't use what we said on the previous slide, that the more mass affects the temperature change. So what is really going on here is that each substance has a certain amount of ability to kind of store heat, and that is called your specific heat. And if you look here for mercury and for water, which one can store more heat? Well, water. So since water can store more heat, you have to add a lot more heat to it to raise its temperature. And this is kind of why the states that are on the coastal parts of the United States, their temperatures don't do the extremes. They're more tempered. But like say you live in a desert, during the day it's super hot and at night it's very cold because there is no water there to kind of temper the temperature. So let's talk more about this ability to store heat. And that is called your heat capacity and specific heat. So the amount of energy required to raise the temperature 1 degree, now that degree could be in Kelvin or Celsius, they're interchangeable, okay, is the heat capacity. So it's the ability to kind of, I like to think of it as the ability to store heat, okay. If the amount of the substance heated is 1 gram, then you can call it your specific heat. If the amount is 1 mole, then it becomes your molar heat capacity, okay. And the units for specific heat can be joules divided by grams Kelvin or joules divided by grams degrees Celsius. If we're talking about molar heat capacity, then instead of grams, you need to have moles in there. So, how do we calculate our specific heat? Well, I don't know if you remember from Chem 1 days, Q equals MC delta T. You could rearrange that, and here is your, C is your specific heat. You take your heat divided by your mass and your change in temperature. So if we want to actually do some measurements, then we have to do something called calorimetry. And calorimetry is how we measure delta H, okay? And it's really measuring heat flow. That is what calorimetry is doing. And in order to do that, we have to use a calorimeter. The calorimeter, you could get very fancy and they're very expensive, or like the one we used in Chem 1, it was just a styrofoam cup, or in this case, 2 styrofoam cups. You have your solution inside, and you have a lid, you have some way to stir it, and you have a thermometer in there. So what do we use calorimetry to find? Well, we could find delta H of the reaction. We could also use it to find the specific heat of an unknown, or we could find delta H of a dissolving process. Since most of our calculations are going to occur at constant pressure or 1 atmosphere pressure, whatever the pressure of the environment is, we could do constant pressure calorimetry. Okay? And what this basically equates to is that the heat change for the system can be found by measuring the heat change for the water in your calorimeter. Okay? And remember, we know the specific heat for water. That is very well documented. And by the end of this chapter, you'll just have that number memorized. So we can calculate delta H of the reaction using this. Basically, your Q of the solution is going to equal negative Q of the reaction. Whatever heat the reaction is losing, the solution is gaining. Or whatever heat the reaction is gaining, it's taking it from the solution. So we use this negative sign to show that. What one loses, the other gains. And that we just show that again here too. And basically this is all because of the first law of thermodynamics, which says that you can neither gain or lose energy. Energy has to be conserved, so it's getting transferred from one to the other. So your system is transferring energy to the surroundings and vice versa, and we show that it's getting transferred with this little negative sign here. And because everything's happening at constant pressure, our Q of reaction is equal to delta H, which remember was enthalpy of the reaction. So what data do you think you would need to collect to complete a calorimetry experiment? Okay, well, you would need to know the mass of the water in your cup, the mass of whatever substance you're adding, your initial and final temperatures, and if you're assuming water, you're going to need to know C of the water. And what would be your major source of error? Well, we're assuming all the energy is transferred from one to the other. We never talk about how much energy gets transferred to the calorimeter itself. So your calorimeter can absorb some energy. And in our next video, we'll learn how to calibrate our calorimeter. And that's basically answering this last. How can you correct for this error? You could kind of measure how much energy your calorimeter absorbs. Or you could calibrate it. The fancy word is calibrate. All right, so let's do some practice problems. So in this first one, you have the specific heat of glycol is 2.42, and it's asking you how many joules of heat are needed to raise the temperature of 62.0 grams of this ethylene glycol from 13.1 to 40.5. So let's list what we know. We know our specific heat. Q is, when they're asking how many joules of heat, remember heat is Q. We don't know that. We know the mass, and we have our change in temperature. So then we could use our Q equals MC delta T equation, plug everything in, and get our answer to 3 sig figs. All right, let's try this one. This one here says that you have a 3.88 gram sample of ammonium nitrate dissolved in 60 grams of water. It's in a coffee cup calorimeter, which is just a styrofoam cup. The temperature drops from 23 to 18.4. Calculate delta H for the solution process per 1 mole of ammonium nitrate. Assume the specific heat is that of pure water. All right, so let's list everything we know. We have our mass of ammonium nitrate is equal to 3.88 grams. And our mass of the water is equal to 60 grams. So since this is dissolving, the sodium nitrate is dissolving in the water, then our total mass is the sum of these two. And that's only because it's dissolving. Okay? Now we have our change in temperature. It's always final minus initial. And that gives us a negative 4.6 degrees Celsius. And you know C of the water is 4.184 joules per gram degrees C. We also know that Q of the surroundings will equal negative to Q of the system. The energy the reaction is losing, the water will be gaining, and vice versa. So let's calculate Q of the water, or the solution, basically what's inside the surroundings. So Q of the surroundings is going to be equal to our total mass times Cp of the water times our change in temperature. Remember, our equation is Q equals mc delta T. Okay, so this is telling us that Q of the surroundings is negative 1200 joules. Because Q of the surrounding is negative 1200 joules, Q of the system, which is really what we're interested in, is a positive 1200 joules. Okay, and it makes sense because your temperature is dropping of the water, which means that the system is gaining energy, right? So now that we have that, it's asking for delta H in joules per mole. So I have to convert my ammonium nitrate into moles. And then I just, to get delta H, I do 1200 joules divided by, and I get 25,000 joules per mole, or 25 kilojoules per mole. Okay, so this solution process is endothermic. Heat is going into it, okay? And it's going in from the surroundings. So the surroundings was exothermic. That's why you could do this, right? Because the heat's flowing from one to the other. All right, and this is our last example we're going to try together. Determine the final temperature when a piece of iron, so the mass of your iron, and your initial temperature of the iron is 85 degrees C, and it's placed in 75 grams of water, and its initial temperature is 20.0 degrees C. C of iron is 0.450. C of the water is 4.184. TF is our unknown. Okay. So what you need to realize is the heat that the iron is losing is equal to the heat that the water is gaining. So we have to put this little negative sign here showing that one is losing, the other is gaining. And now we could set our equations. Remember, Q is MC delta T equal to each other. So on the left, we'll do the iron. So we have 25 grams of iron times its CP times T final minus the initial temperature equals the negative of the water. T final minus its initial temperature. And now we do a little bit of algebra. Distribute. Combine like terms. Divide, and we find that TF is equal to 22.2 degrees Celsius. Okay, so that was kind of like two Q's kind of coming together in equal and opposite signs. All right, well, that's it for now.